Assalamualaikum and hi everybody. In this video, I will share with you an introduction to a chapter on test of hypothesis or hypothesis testing in engineering statistics course. In this course, we cover this area in chapter 4 after chapter 3 on estimation. This first topic under the chapter will only focus on an introduction to test of hypothesis. Let's go to the next slide. Before we go further into the content of this topic, let us look at the learning objectives first. At the end of this topic, you should be able to be familiar with common terms in the test of hypothesis. You should also be able to identify different types of hypothesis tests. You should also be able to define different types of errors you might be doing in running a hypothesis test and the corresponding probabilities related to each of the errors. And finally, you should be able to list down the procedure of a hypothesis test. Let's look at some common terms that you should be familiar with. The definitions of these terms are available in the Statistics for Engineers textbook, pages 81 until 84. Definition of these terms are also available in many other references. Now let's look at the first term, a statistical hypothesis. What is it? It is defined as a statement about a parameter of interest if you are interested in a single population parameter, or a statement about more than one parameter of interest if we are interested in more than one population parameter. What do we mean by a statement about a parameter of interest? Here, we may say that a parameter may take or may have or is claimed to have a particular value. We cannot prove that this statement or hypothesis is absolutely true or false. It depends on the sample information or sample data, whether the sample data provides some evidence to support or reject the hypothesis we are making about the parameter of interest. So, a statistical hypothesis is a statement about a parameter of interest where the parameter could be assumed to have a particular value. Different from chapter 3, where a parameter does not have a value, so you want to estimate the parameter. Here, however, a parameter could be assumed to have a certain value, but you want to test whether you have enough evidence to support or reject the hypothesis that the parameter has that particular value. Now, the next terms are the null and alternative hypothesis. A null hypothesis is denoted by H0, whereas an alternative hypothesis is denoted by H1 or HA in some other references. What is a null hypothesis? A null hypothesis is an assertion about one or more population parameters. We hold this assertion as true until there is a sufficient statistical evidence to say otherwise. What about alternative hypothesis H1 then? H1 is an assertion of all situations not covered by H0. For example, suppose under H0, we claim that mu, a population mean, is equal to 10. A possible H1 will be mu is different from 10, or mu is not equal to 10. Here, any values different from 10 is not covered under H0 but under H1. If we reject H0, we may say that we have a sufficient evidence to reject H0 in favor of H1, meaning if we reject H0, we are saying that we have evidence that mu is not 10. Okay, if we reject H0, it means we have sufficient evidence to support the hypothesis that mu is not 10. The next important term you need to know is a test statistic. What is a test statistic? It is a sample statistic computed from the data obtained by a random sampling. The value of a test statistic can be used to determine whether or not a null hypothesis should be rejected. A choice of a test statistic depends on what parameter you test. For example, if you test a single population mean mu, then you can either have a z-test statistic or a t-test statistic. If you test a single population variance sigma squared or a single population standard deviation sigma, then you should use a chi-square test statistic. If you are interested in testing the difference between two population proportions by 1 minus by 2, say, then you have a choice of z-test statistic, and so on. You may recall what you learned in Chapter 3, Estimation. The choice of test statistics in this Chapter 4 on the test of hypothesis is similar to the choice of statistical scores that you have in Chapter 3 on estimation. However, the test statistics have particular formula which we will learn in detail in the subsequent topics. The next term you will be using very often in this chapter is a decision rule. It can sometimes be called as a rejection rule or rejection criterion. This decision rule specifies a condition under which H0 will be rejected. The condition usually relates to the comparison between the value of a test statistic and a critical value. What is a critical value? Let's look at the next slide to learn about the next common term in this chapter, which is a critical value. Before we look at the definition of a critical value, let's look first at the definition of a critical region. A critical region is a set of values for which the null hypothesis H0 will be rejected. This set of values is from a random variable that assumes the same underlying sampling distribution for the test statistic. For example, if we have a z-test statistic in testing a population mean mu, then the critical region will be a set of z values for which the null hypothesis H0 about the population mean mu will be rejected. Another example, if we have an f-test statistic in testing a ratio of two population variances, then the critical region will be a set of f values for which the null hypothesis about the ratio of population variances will be rejected. Having understood what a critical region is, next we define a critical value. At times we can have more than one critical value. What is a critical value? It is actually a boundary value of a critical region. If we have more than one critical value, then we will have more than one boundary value of a critical region. The critical region and critical value will be clearly demonstrated later using a number of figures in subsequent slides when we look at different types of hypothesis tests. Finally, the last common term that you should be familiar with is the level of significance. It is denoted by alpha. We are talking about the same alpha in Chapter 3 when we have a two-sided confidence interval. Now alpha has a name in this chapter, which is a level of significance or simply significance level. You need to specify at what level of significance you carry out a test of hypothesis. Your decision and conclusion may change at different level of significance. Now, let's look at the types of hypothesis tests. You can have a look at your textbook, page 83. We have three options of hypothesis tests that we can carry out in testing a particular parameter of interest. The first is a two-sided alternative hypothesis. We can use this type of hypothesis if we want to investigate whether there is any change or a difference in the parameter's hypothetical value. The keyword here is a change or a difference in the parameter's hypothetical value. This type of test has a connection with a two-sided confidence interval that we have learned in the previous chapter on estimation. The connection will be further explained later in this topic. The next type of hypothesis test is a one-sided alternative hypothesis test on the right, which can be defined as a right-sided alternative hypothesis, or sometimes we can call it as a right-tailed test of hypothesis. We can use this type of hypothesis test when we aim to investigate if the parameter's hypothetical value has increased or has become larger than before. So the keyword for a right-sided alternative test is increase or becomes larger or has risen, or any word that shows an increase in the parameter value. The third and last type of hypothesis test is a left-sided alternative test, or we can simply call it as a left-tailed test or a left-sided test of hypothesis. We can use the left-sided alternative hypothesis test if you are interested in testing whether a parameter's hypothetical value has decreased or reduced or has become smaller than before. So the keyword in this left-sided test is decrease, reduce, or decline, or any other word that describes a decrease in value. These three types of hypothesis tests will somehow influence the choice of critical region and hence the critical value in a certain statistical testing procedure. Therefore, it is crucially important to identify clearly which of the three tests we should carry out when testing a particular population parameter. Let's look at a two-sided alternative hypothesis test closely. Suppose a parameter denoted as theta is claimed to have a value theta naught. We want to test if there is any difference or any change in the theta value. Here we write h naught followed by a colon and followed by theta equal to theta naught. The next line is h1 followed by a colon and followed by an expression theta is not equal to theta naught to show that we are testing a difference in the theta value. We then write the decision rule. Reject h naught if the chosen test statistic denoted by Ts in this slide is less than a left critical value at alpha over 2, or if the test statistic is greater than a right critical value at alpha over 2. Notice that a two-sided test, we must use alpha over 2 for the two critical values on the left and on the right of underlying distribution from where the test statistic is defined. We look at an example in this two-sided test in the next slide. Suppose data from the previous slide is a population mean mu, which is our parameter of interest that we want to test. We want to investigate if sample data provides any evidence that mu is different from a value, say mu naught in this example. Here, the notation mu naught can be any real value. Therefore, we can write the null hypothesis H naught like this. H naught followed by a colon, followed by a statement about the parameter of interest, which is mu equal to mu naught. The alternative hypothesis H1 can be written like this. H1 followed by a colon, followed by mu not equal to mu naught. Notice that under H0 we always have equality sign mu equal to mu naught. Whereas under H1 we have an inequality sign in this example since we want to investigate if the mu value is different from mu naught or has changed from mu naught. So the statement under H1 is mu not equal to mu naught. Therefore, we have a two-sided test. In this two-sided test, we should have two critical regions and two critical values, each at alpha over 2. Hence, a possible decision rule or rejection criterion in this example then is reject H0 if Z test is less than negative Z alpha over 2. That's on the left, or if Z test is greater than Z alpha over 2 on the right. You can see alpha over 2 on the left and on the right of the curve shown by the shaded regions under the Z distribution from which the Z test is defined. The two critical values, negative Z alpha over 2 and positive Z alpha over 2, can be shown as the boundary values of critical regions. The first critical region is the set of Z values below negative Z alpha over 2, whereas the second critical region is the set of Z values above Z alpha over 2. The Z values in the middle between negative Z alpha over 2 and positive Z alpha over 2 are what we call the acceptance region. Just to note that you must calculate Z test first based on sample data and observe where the Z test value will fall into before you make a decision to accept or reject H0. If the calculated Z test is in any of the critical regions, that is, if Z test is smaller than negative Z alpha over 2, or if it's greater than Z alpha over 2, we will reject H0 in favor of H1 and conclude that the population mean mu is different from or not equal to mu naught. However, if Z test falls in between the critical values, that is, if it falls in the acceptance region, then we do not reject H0, or we say we fail to reject H0 and conclude that we do not have sufficient evidence from the sample data that mu is different from mu naught. In this slide, we look at a one-sided or one-tail alternative hypothesis test on the right, or simply right-tail or right-sided test closely. We use the same generic parameter denoted by theta, which is claimed to have a value theta naught under H0. Again, theta naught can be any real value. Here we want to test if there is any increase in the theta value. What we can do first is to write H0 followed by a colon, followed by a statement theta equal to theta naught. Next is writing the alternative hypothesis H1, followed by a colon, and followed by a statement theta is greater than theta naught. Notice that under H0 we only have equality sign, whereas under H1 we have a greater than sign, where we do not have equality sign under H1. We cannot simply put theta is at least bigger than theta naught. It has to be theta is greater than theta naught. So we use notation greater under H1. Next is to write the decision rule. Here the decision rule will be reject H0 if the chosen test statistic is greater than the right critical value at the level of significance alpha. Notice that for a right-sided test, we must use the whole alpha value for the right critical value of the underlying distribution from where the test statistic is defined. Use the whole alpha value instead of alpha over 2. Let's look at the next slide for a simple illustration. We use a population mean mu again as our parameter of interest to illustrate a right-sided test. In this illustration, we want to investigate if sample data provide any evidence that mu is greater than a value, say mu naught. Again, mu naught can be any real value. Therefore, we can write the null hypothesis H0 like this. Mu equal to mu naught under H0. The alternative hypothesis H1 can be written like this. H1 followed by a colon followed by mu is greater than mu naught. Notice that under H0 we always have equality sign mu equal to mu naught, whereas under H1 we have a greater than sign. In this example, since we want to investigate if the mu value is greater than mu naught or has increased from mu naught, so the statement under H1 is mu is greater or bigger than mu naught. Thus, we have a one-tail hypothesis test on the right or the right-sided test. In this right-sided test, we should only have one critical region and one critical value on the right of the underlying sampling distribution at alpha level of significance. Therefore, a possible decision rule or rejection criterion in this example is then reject H0 if Z test is greater than Z alpha on the right. You can see alpha on the right of the curve shown by the shaded regions. The critical value, which is Z alpha, can be shown as the single boundary value of the one critical region defined by the set of Z values above or greater than Z alpha. The set of Z values below Z alpha is what we call the acceptance region in this illustration. Please note again that you must calculate the z-test value first based on the sample data and observe where this z-test value will fall into before you make a decision to accept or reject H0. If the calculated z-test is in the critical region, that is, if z-test is greater than z-alpha, we will reject H0 in favor of H1 and conclude that the population mean mu has increased or become larger than mu0. However, if z-test falls in the acceptance region, that is, if z-test is smaller than z-alpha, we can decide not to reject H0, or we fail to reject H0 and conclude that we do not have sufficient evidence from the sample data that mu is greater than mu0. This slide shows the last type of hypothesis test, which is a one-sided or one-tailed alternative hypothesis test on the left, or simply left-sided or left-tailed test. Again, we use the same generic parameter denoted by theta, which is claimed to have a value theta0. Theta is any population parameter we want to test. In this chapter 4, theta can be mu or pi or sigma squared or any parameter of interest. Whereas theta0 can be any real value. Here we want to test if there is any decrease in the theta value. First, what we need to do is to write H0 like this. H0 followed by a colon and next followed by a statement theta is equal to theta0. The next line is H1 written like this. H1 followed by a colon and followed by the expression theta is less than theta0. We then write the decision rule. Reject H0 if the chosen test statistic Ts is less than a left critical value at alpha level of significance. Notice that for a left-sided test, we must use the whole alpha value for the left critical value of underlying distribution from where the test statistic is defined. For a simple illustration, let's proceed to the next slide. In this last illustration, we use a population mean mu again as our parameter of interest to illustrate a left-sided test. This time, we want to investigate if sample data provide any evidence that mu is smaller or less than a value, say mu0. Again, mu0 can be any real value. Therefore, we can write the null hypothesis H0 like this, and the alternative hypothesis H1 like this. Notice that under H0 we always have equality sign again, which is mu equal to mu0, whereas under H1 we have a less than sign in this example, since we want to investigate if the mu value is less than mu0 or has decreased from mu0. So the statement under H1 is mu is less, lower, or smaller than mu0. Therefore, we have a one-tailed hypothesis test on the left, or simply the left-sided test. In this left-sided test, we should also have only one critical region and one critical value on the left of the underlying sampling distribution at alpha level of significance. Therefore, a possible decision rule or rejection criterion in this example is then reject H0 if z-test is smaller than the negative z-alpha on the left. As we know, z distribution is centered at 0, therefore the left-sided critical value will be negative. You can see alpha is on the left of the curve shown by the shaded region under the Z distribution from which the Z test is defined. The critical value, which is the negative Z alpha, can be shown as the single boundary value of the one critical region defined by the set of Z values below negative Z alpha. The set of Z values above negative Z alpha is what we call the acceptance region. Please note again that you must calculate Z test first based on sample data and observe the location of Z test value on the horizontal axis before you make a decision to accept or reject H0. If the calculated Z test is in the critical region, that is, if Z test is smaller than negative Z alpha, we will reject H0 in favor of H1 and conclude that the population mean mu has decreased or become smaller than mu naught. However, if Z test falls in the acceptance region, that is, if Z test is larger than the negative Z alpha, we can decide not to reject H0, or we fail to reject H0 and hence conclude that we do not have sufficient evidence from the sample data that mu is less than mu naught. Or we can simply say we do not have enough evidence to conclude that mu has decreased in value. Please watch the next video on the continuation of this introduction topic under Chapter 4 on Test of Hypotheses. The next video will define and explain the types of errors one can possibly do in running a hypothesis test. The next video will also highlight the procedure to carry out a hypothesis test. Until then, thank you very much for watching. Assalamualaikum and see you again in the next video.